Hello, everyone, and welcome to today's webinar on the future of consumer packaging, driving sustainability with machine learning technologies. My name is Peyton Weston, and I'm thrilled to be here with you today. I'm joined by my colleague, Will Irwin, who will be taking over later in the session. Together, we'll be exploring how AI and machine learning can transform how we design and deliver packaging solutions, especially in the face of sustainability and regulatory challenges. At Citrine, our mission is to enable product experts with cutting-edge AI. We make it possible to accelerate innovation with machine learning without requiring teams to become data scientists. Our platform learns from small data sets and expert knowledge to help organizations push into new frontiers and tackle their most pressing R&D challenges. We do this by combining a robust AI SaaS platform with technical services. This means our customers don't just get software. They also get expertise and guidance on how to fully transform how they approach product development. Citrine was founded in 2013 with headquarters in Redwood City, California. With over a decade of AI implementation experience, we've had the privilege of partnering with the world's top materials, chemicals, and consumer goods companies. In fact, among our customer base are some of the top players in adhesives, sealants, specialty chemicals, and personal care, leaders who are setting the pace for sustainable innovation. Now, let's talk about what makes packaging such a challenging space. Companies are constantly balancing competing performance objectives like strength, barrier properties, cost, and weight. At the same time, they face evolving regulations, increasing sustainability mandates, and unpredictable supply chain volatility. This creates a complex environment where conventional methods simply can't keep up. Because traditionally, innovation meant lots of trial and error in incremental progress. But when you're juggling multiple objectives and constraints, along with timeline pressures, you can't test every formulation or design. That's where AI makes a real difference. Instead of being limited by what you can test, AI helps take a look at the full space of possibilities and quickly zero in on your most viable options. The result is not only better, more cost-effective products, it's also dramatically faster development. Our customers typically see a 50 to 80% reduction in experiments compared to traditional methods, like DOE. This means they can accelerate time to market, balance more objectives simultaneously, and adapt to respond faster to new regulations or market shifts. The business benefits are clear: accelerating sustainable innovation while meeting consumer preferences, reducing costs by improving R&D productivity and reducing waste, and building resilience to adapt quickly to supply chain disruptions and evolving regulations. To bring this to life, let's take a look at a real-world example. A global materials conglomerate needed to remove the PFAS in their adhesives. This was a huge compliance and performance challenge. Using Citrine, in just 6 months, they were able to successfully reformulate, saving over 2 years of R&D time in what was originally a 5-year project timeline. This is just one example of how Citrine and AI can accelerate innovation and product development in a meaningful way. So, how does this work? At its core, our platform uses an iterative workflow. Starting with the data that your teams already have: historic data, experimental data, material properties, processing conditions. Using that in tandem with your team's domain knowledge, an AI model is generated without any coding required. Guided by your goals, a search space is generated that helps tell the AI where to look for formulations. After setting target properties, a list of ranked candidates is generated for your team to review. Based on your goals and project, your team will select the most promising candidates and bring those to the lab. After testing them, those results will be fed back into the model to improve the predictions and generate the next set of best candidates. Through the cycle, the workflow converges quickly on solutions meeting multiple objectives. What normally might take hundreds of experiments can be done in a fraction of the time. Citrine is not about replacing scientists. It's about supercharging their intuition and allowing them to focus on solving problems instead of being stuck in an endless loop of trial and error. At this time, I'm going to hand it off to my colleague Will Irwin, who will take a deeper dive into how this workflow applies to packaging optimization and share a live demo of the platform. Over to you, Will.
Thanks, Peyton. So now let's get into the demo. And in this demo, we'll discuss multi-layer packaging optimization. So here we're looking to balance several competing objectives in this multi-layer packaging product. We're looking to have a product that is biodegradable and meets consumer and regulatory demands, has sufficient barrier properties, so protecting against moisture, oxygen, contaminants, optimizes production cost. We're looking to have processing parameters that are efficient for cost reasons. Of course, limiting weight as well, making a material that has minimal mass while maintaining structural integrity. And finally, we're looking to optimize for mechanical strength. So ensuring that we have a durable product that can survive the supply chain and product lifecycle. So now I'll move to the Citrine platform and we'll begin the demo. So here we are in the Citrine platform. In the Citrine platform, we have 4 distinct elements. Training sets, which represent the data that you will use to train your model. This typically comes from your organization, your team. These are the experiments you've done in the past. The AI model, which is ultimately making a mapping of the inputs, the processing parameters and compositions of your films, and serves to predict the outputs, things like the biodegradability, barrier properties, and such. Once you've built a model, you then develop a search space, and the search space represents the hypothesis that you want to explore. You'll put bounds on the composition, bounds on the processing parameters that you would like to explore. And finally, we get to candidates. Candidates represent these actual experiments that you might do. And we have the sort of inputs, the composition, the processing parameters, and the outputs, the predicted values of the goals that we have. So I'll walk through each step of this so we can see what it looks like in the Citrine platform and how this iterative learning process works. So we begin with data. We're looking at a training set here. And the way that we got this data into here was we put it in Excel or a comma-separated values file, and we ingested it into the Citrine platform via the UI. And I won't show that portion. I'm just showing this part where we have the visualization of this data. Now, oftentimes, this is the first time that our users have seen all of their data in one place. They can use this to look at trends in their data, and also to audit their data and make sure that it represents what they think it would represent. So here in these multi-plots, we can see sort of the trends of different variables in our data and understand, do this exploratory data analysis. We can also go in and look at our data along different axes. We can look at, for instance, the distribution of our data. Here we've got the distribution of the completion of biodegradation for all of our samples, where most of them fall in this 40 to 95% range, but we've got some outliers here in the sort of 5 to 20% range as well. This allows you to see what your data looks like, understand these trends, but also understand if any data has been entered wrong or if there is some error in the data. Now, this is the tabularized data that we'll actually use to train our model, but I want to quickly look at a material history. When I say material history, this is Citrine's method of collecting data and looking at it that is ultimately materials aware. So what we're seeing here is actually the full diagram representing the generation of one of these plastic films. So on the left-hand side, we have the acquisition of these raw ingredients, which may have some properties. For instance, the ethylene glycol here has molecular weight, density, and a chemical structure associated with it, which we will use later on in modeling. We mix those ingredients together to form these intermediate ingredients. And finally, we co-extrude them to make our final packaging film, which has a set of properties as well. The elastic modulus, biodegradation, and so on. So here, the way I think about the material history is this is all of the information that you would need to reproduce this experiment in the future. So we're, in addition to an AI tool, we are a catalog for all of your experiments that are searchable and that your entire team can access and understand what experiments have been done in the past, and ultimately this cuts down on repeated experiments and waste. So now let's get back to the core workflow. Once we've generated a training set, it's time to build an AI model. Now, generally, we can build an AI model with one click, and that is built automatically based on the training set. And I'll look at this model that we've built and we've already trained and explain some of the core components. So what we see here is these boxes that are linked to each other. At the top, we have our raw training data. And then we've got a series of these blue boxes, which represent the generation of features. For instance, we've got a molecular structure featureizer. This takes those molecular structures that we've put into our data and generates a set of numerical features that describe those structures and can be used downstream in our modeling. We've also got our mean properties node. This computes the average of properties of our raw ingredients so that they can be used to predict the behavior of our final materials. We, of course, also leverage ingredients and labels. The ingredients are, of course, just the components that we have, and labels represent the role of those ingredients. So how much of my final formulation is, for instance, PLA or PEF. Now, we also can build these custom formulas. So your rules of thumb that a product developer might take into account, we can add those to our models as well. And in this case, we've built in the package weight, which we can get by multiplying the density times the thickness. But you can express any sort of formulas in these graph models to really add your domain knowledge into the modeling. And finally, these purple nodes represent the actual machine learning models. So here we've got an output that we define that we would like to predict, and a set of inputs that we can use to predict those outputs. And once we've built a model that represents our domain knowledge, we can go in and evaluate that model. Here we see a summary of how this model is performing, where on the left-hand side, we see the R-squared value for each parameter that we'd like to predict, where 0 sort of represents no signal, 1 represents a perfect model. And in addition to auditing how that material performs, or how that model performs, we can get insights into why the model is performing in this way. If I look at this feature importances on the right-hand side of my screen, I can see that the extrusion temperature is a major driving factor in the daily biodegradation rate. I can also go in and get an even more nuanced understanding of how the model is interpreting this impact. So with this feature impact plot, I'm seeing that when the co-extrusion temperature is low, I have a higher biodegradation rate. I'm contributing positively to my biodegradation. As my co-extrusion temperature increases, I'm going down and I'm decreasing the biodegradation rate. So this can be a tool to both understand your model, but also for product developers to generate hypotheses and understand how they might like to change their experiments and develop optimal materials. So once we've generated a model, the goal here is not to develop a perfect model. The goal is to develop high quality materials that perform according to your set of goals. And we do that by developing a search space. Now, our search space represents sort of our hypothesis space. And in the first tab, we're defining the ranges on the labels and ingredients. Now, labels I mentioned earlier are the categories of ingredients, or sort of the types of ingredients that we're including. And we've got 4 types of ingredients here: the PEF layer, the PLA layer, mycelium-based layer, and the starch-based layer, which are all contributing different things to the final product. And we can then specify the ranges in composition of how much of my final product do I want to be mycelium or PEF. I can also define my ingredients here as well. So if I go in, if I wanted to include specific parts of the mycelium base layer or specific elements of it, I can include or exclude those based on either my scientific needs. I want to try something which explicitly includes or excludes an ingredient, or business needs. If a material is missing from production, we can't make the material, we can exclude that and reformulate. Or if a material is banned from a market that you're selling into, we can just exclude that at this stage. Additionally, we've got the other parameters tab here. These are the processing parameters associated with your material. So you can see here, we've got the co-extrusion of multi-layer film, speed, where we're choosing to allow it to search between 10 and 50 meters per minute. We here are defining all of the different parameters that go into making this material, the speeds, the temperatures, the thicknesses, the humidity. And we're going to search over all of these dimensions to find the optimal set of parameters for your material production problem. Now that we've defined a search space, we have all of the elements we need to surface high quality candidates. Now, candidates are the proposed experiments that will have a high likelihood of achieving the goals that we set. So what we're looking at here is 500 distinct candidates that do not exist in our training data. These candidates are novel formulations that we have a set of inputs for each one, the compositions and the processing parameters, as well as a predicted set of outputs. And the logic here is that we have given the platform 4 goals: a water vapor transmission rate of less than 10, a final film tensile strength of 70 or above, a biodegradation completeness of above 70%, and a package weight of below 5. Now, we've got 500 candidates here. So we may want to narrow those down further, because we're not going to take 500 experiments into the lab. We're going to choose a handful of them. So we can do that by filtering. And we mentioned that one of our goals is to keep the processing inexpensive and minimize those high temperatures. So here we can filter to which of these candidates have a final extrusion temperature under 165 C. So we're filtering on the process. We can also filter on the mycelium layer. In this case, we're saying, okay, we want up to 10% mycelium layer, but otherwise we want to exclude these. So we're down selecting among these 500 candidates to see the number of candidates that meet these additional conditions. Now, our top candidate falls under our top filter, or our first filter, that less than 165 C. So let's take a look at the details of this candidate. Now, at the top of the page, we see the predictions for our candidate's performance against the goals that we have. So if you remember, our goal of biodegradation was to be above 70%. This has a predicted outcome of 81 plus or minus 7. So we can be reasonably sure that if we make this candidate, we will achieve that 80% or above 70% biodegradation completeness. So it's helpful to know here that we not only have the prediction for the value we expect, but we also have the uncertainty. We can understand how likely our candidate is to actually achieve the behavior that we're looking to achieve. We've got all of these dimensions that we can look at, and we can see cumulatively how likely are we to achieve all of these candidates or of these goals, and that's ultimately what that score comes from that we were looking at. Here, we can now see, okay, what are the elements that we need to do? How do we actually make this candidate? Here, we've got the composition of this. So we've got 5 raw ingredients, which are in these 5, or in these amounts defined here. We can change the basis of this. So if we just want to look at it in percentage, it's 81% polydilactide, and so on. Now, there were some other parts to our process as well, which were these processing parameters, the speeds, the temperatures, the thicknesses, and such. And we've also got those specified here. And so this is the full set of instructions that you would need to take this into the lab and to ultimately generate something that has these predicted outcomes. Now, our model has a high degree of confidence, but you see varying levels of uncertainty here. So we don't expect our model to hit these parameters exactly. And that's where this iterative experimental learning comes in. Once we have made this candidate in the lab, we can go in and we can put our actual ingredient inputs that we took to the lab, the processing parameters, and the measured properties, and we can record this for training. And then we go back through that loop and we retrain our model with the data that we've gotten from the candidates, and we're honing in on those high quality areas of our search space so that we can quickly and decisively make high quality films without having a lot of the guesswork that you might have in intuition driven experiments. So this concludes the demonstration of the Citrine platform, and I will pass it back to Peyton now.
Thanks, Will. That was a great demo. Now I want to zoom back out and talk about the competitive advantage of adopting AI for packaging and product innovation and optimization. One of the most exciting aspects of this technology is that it can scale for companies of all sizes. Smaller companies can use AI to reduce research costs and tailor products to niche markets, allowing them to compete with the bigger players. Mid-sized companies benefit from their agility with AI. They can test, learn, and scale quickly, often leapfrogging the competition. And large companies can take advantage of their bigger data sets, applying transfer learning across teams and divisions to accelerate innovation at scale. No matter where you are on the value chain, AI adoption isn't just about efficiency. It's about creating sustainable competitive edge. Our team not only brings an AI platform that's easy to adopt, we also bring the expertise to guide R&D teams through the process of using it effectively. If you'd like to continue the conversation, we'd love to connect, whether that's at an upcoming industry event or over coffee, virtually or in person. Please feel free to reach out to us directly. On behalf of myself and Will, I'd like to thank you for joining us today. We are excited about the future of consumer packaging and the role that AI plays in building a more sustainable, resilient, and innovative industry. With that, let's move on to our live Q&A session. We would love to hear your questions.